second last class. I'm a little sad, but more happy that things are coming to a close. As we've all known and seen, this is quite an intense class. And just a heads up, this class and Thursday's class are the most intense. So let's just keep our heads together and get through these. All right, so today what we're going to do is we're going to look at two problems with kinetics where we're looking at moments and forces with rigid bodies. And then we will, if we have time, hopefully we will have time, we want to start some theory on the last portion of kinetics, which is the conservation of energy and the conservation of momentum and things like that. So let's get into it. So the first thing that we're doing here is looking at this problem here, whereby you've got, by the way, can everyone, I know this might be a little late, everyone can hear me okay and see the screen okay, right? All good? All right. So whereby we've got this 9 kilogram uniform disc, and it's attached to this slender rod AB by means of frictionless pins at B, and also there's another pin at C which has contact with it's coming through from the disc and has contact with the rod, and it's rotating in a vertical plane, which basically means that gravity is obviously acting downwards, and there is a moment that's applied to the rod AB, which is causing this motion to happen. And at this particular instant that you're shown, you're told that the assembly has an angular velocity of 6 radians per second and an angular acceleration of 25 radians per second squared, both of them counterclockwise, right? So that works out for us because that's in the positive k hat direction. And you're asked to find the moment M, right? And then you're asked to find out the force exerted by the pin C on the member AB. All right. So we have to do two different things to the problem. For part A of the problem, when you're looking at couple M, which is working on the whole assembly, we're going to look at the whole assembly. And then when we're looking at the force exerted by the pin on the member AC, we're just going to look at the disc, and that's going to make things easy for us. All right. So with that, let's get started. So looking at the part A, we want to see the whole assembly, right? And the thing to know, guys, when you're looking at the whole assembly and you're looking at your forces and your moments, it's always better when the problem just asks you for what the moment is, to just do moment, to just look at the moment expression. Because if you look at the forces expressions, then you will have to find out what the unknown reaction forces are as well, right? And that's just adding extra things that you're doing to the problem. We just want to set up the free body diagram and kinetic diagram and then solve the problem in the quicker, most prudent way, right? And whenever they ask you for a couple, you should just take the moments about the point where you have the most reaction forces so that you don't have to worry about finding out what those are, all right? All right, so with that, let's get into it. Oh, before we get started, always forget frame of reference, right? X, Y, and Z. So we'll say that that's in the positive direction. All right, so first things first, when we're looking at kinetics, when we're looking at the whole assembly, what do we have to do? What's the first step? Step number one. No one?
Like just a free body diagram of
Free body
like
diagram. Exactly, free body diagram. And in dynamics, it's, what is it? Free body diagram and kinetic diagram, right? So that's what we're going to do. So let's say that that's the rod. That's the disk. So that's for my free body diagram. And that's equal to rod. Terrible drawing, but we'll go with it. All right. Then for all the forces that are acting on the body, right, with the pin on top, you're going to have the reaction forces, right? So you'll have AY and AX, right? You will have the weight of the disk, right? So let's call that WD. You will also have the weight of the rod, right? Let's call that WR. You have your applied moment, right there. And then because we're looking at the whole system, we don't need to worry about the pin in this case for the first part of the problem, right? Because we're looking at the whole system. So we only need to worry about the forces acting on the system, because the force that's acting on the pin. If you look at it, the whole system, what's it going to be? You're going to have one internal force and you're going to have one external reaction force, right? Each force has an equal and opposite reaction. So those just cancel out when you're looking at the whole system. So don't need to worry about that. All right, so that's all of the forces in here. And just to make our life easier, right, because we're going to have to do moment equilibrium, let's just find out what the distances are as well. So you're told in the problem that the angle is 30 degrees. This length is 500 millimeters, right? So what you can say is that this length over here is going to be 500 sine 30, right? So that's just equal to 0.25 meters. Just converting everything into meters because that just makes life easy, right? So this is equal to 0.5 times sine 30, right? Because this length here is equal to 500, so that's 0.5 meters. This angle is 30 degrees. So this horizontal distance is just equal to sine 30 times that. So that's 0.25 millimeter. From there, you can also say that for the point on the rod on which the weight acts, its center of gravity is going to be at the center, right? So what's this distance going to be? The half distance from the pin to the point there. So 0.125, right? Just half of 0.25. And similarly, that distance is equal to that much. All right, are we good with the free body diagram? Any questions?
Oh, you're saying the weight from the rod is just right at the center, so that's why you're like splitting it in half.
Exactly. Weight always acts at the center. Yeah.
Got it.
All right, so now if we look at the kinetic diagram, now when we're looking at the kinetic diagram, we can be smart about it, right? You can look at X and Y components, but then you end up with too many things, too many unknowns. With a problem where you have pure rotation like this, it makes sense to look at tangential and normal components for your acceleration, because the normal component is going to pass through the point about which you're going to take your moment, and you're left with fewer unknowns that you have to deal with. All right, so for this point, so let's call this point the center of the rod, right? Let's call that point, let's say that that's G, right? So that's the point G there. So let's say so that's the corresponding point. Yeah, drawing was terrible. Let me just draw that again, guys. Give me a second. All right, so let's say that's the point G over there, and here you have the point B, right? So that's your point B. So now what I'm saying is that you want to look at the normal and tangential components of your acceleration, because that makes solving the problem a little bit easier, right? So over here, what I mean is, let's say if the for the disk itself, right, you will have, and also when we're looking at two different bodies from the theory of that we looked at in kinetics, you want to look at the bodies separately. Otherwise, you'll have to find out where the centroid is and then do the work about that, right? To just make your life easy, it's okay to separate the two bodies. So you're looking at the disk and the rod separately, all right? So let's say for the disk itself, and always remember, you're looking at what's happening at the centroid, all right? So the mass of the disk times the acceleration of the disk and the tangential component of that, and then you're going to have the normal component, but we're not worried about it because it's going to pass through the point that we're going to be solving the problem about. All right. Then for the point G, you have the mass of the rod times the acceleration of the rod in your tangential direction, like that. You're obviously going to have a normal component as well, but again, we don't need to worry about it. Right, and this was point A. All right. Are we good with the kinetic diagram?
Yep.
We're not. We're missing something, right? Because there is rotation that's happening, you're going to have an I alpha term where I is your mass moment of inertia, and you're always looking at that about the centroid of the bodies that you're looking at. So here you're going to have one term for the disk. So let's say that that's ID alpha like that. And you're going to have one for the rod. Let's say that that's let's call that IR alpha. And because they're connected and they're moving together, the angular acceleration is going to be the same. All right, is that clear, guys?
So would the acceleration for the rod and the disk separately for their tangential also be the same?
No, right? Because, and that's a beautiful question, Mr. Simpson. So for that tangential, it's going to be alpha times this distance for the rod, and it's going to be alpha times this distance, the whole rod for the disk. That's what it's going to be.
Oh, okay.
That was a good question. Yeah. And that's the next step. So you preempted what I'm going to do next. All right. So now to get our distances out of the way, we know this one is 500. So we break it up into half. So this distance here is equal to 0.25 meters, and that distance there is equal to 0.25 meters, like that. And you're absolutely right. So this is going to equal alpha times 0.25, right? Alpha r. And this acceleration is going to equal alpha times 0.5 r. And now we're finally ready to do the problem. Now, if the problem was asking you find the reaction forces at the pin A, then you would do force equilibrium. But because the problem is just asking for the moment, the easiest thing to do is to just take the moments about the point A, because then you don't need to worry about these forces. All right, so let's do that. So doing moments about the point A, right? All right, so now let's see, look at the free body diagram side of things. So I have my positive moment, right? M like that. Then I have the component due to my WR, that's going to be negative, right? So minus WR, and we're not using vectors. I'm just straight off using scalars for this problem because it just makes things easy. So WR times 0.125, right? Minus, again, WD, the weight of the disk is also going to be in the negative direction. So you have minus WD times 0.25. Right? Okay. And I believe, yep, that's everything I need from my free body diagram. And that is equal to, all right, so I have obviously get my IR alpha terms out of the way, my I alpha terms out of the way. So I have IR alpha plus ID alpha. And then I have the moments due to these tangential accelerations, right? So now MR AR, so that's going to be positive, and MD, AD is also going to be causing positive moments, the way we've defined them over here, right? So you have plus, and the force there is MR times, and we're because we want lower amount of unknowns, right? So we're going to convert this into alpha. So you have alpha times 0.25, right? So that's my force. Multiply that by the distance to get the moment. Right? And then you have the same term, but for your disk. So that will be MD times alpha times 0.5, which is the acceleration, and then times 0.5 meters again to get the moment. How's it going, guys? Does that make sense?
Yeah, just a quick question for your notation. Like when you have IR alpha,
Yeah.
just to the left of that, you have like these two L's. Is that like just like you're continuing the
Oh,
equation
this
below?
is just an equally. Left-hand side equals right-hand side. This is my free body diagram, left-hand side, and this is my kinetic diagram, right-hand side. That's just an equal to sign.
Okay.
Sorry about that. I just ran out of space here. We're dealing with big equations. Isn't there a meme of that guy like talking about when he the crazy hair with the
aliens.
alien invasions? Yeah, ancient aliens. Yeah. Anyways, you guys have any questions with this equation? Basically, we looked at the tangential and the normal components of the acceleration because we can write those accelerations in terms of the angular acceleration, right? We know the tangential component is just equal to alpha times r, and the problem tells us what alpha is, right? So you can go ahead and then solve the problem. Why? Because let's take a look. WR, the weight, is known. Distance is obviously known. WD is known. IR and ID, I can find out, right? Those are just the mass moments of inertia about the centroids of the rod and the disk. Alpha is given to me in the problem, right? MR is the mass of the disk, which is given in the problem. Mass of the rod given in the problem. Angular acceleration is given again, and these are just the distances that are known. So you have one expression for one unknown. All right. Now, you guys are like, Ashish, you're crazy. How do we know this without doing this, without practicing it? That's it. You have to practice yourself. But, and you can take a mental note that whenever you have pure rotation, just like consider using the tangential and the normal components of the acceleration, especially in a kinetics problem, because that will make your life slightly easier. Now, you could have taken the XY components and solved the problem, but then you would have had to do more things to find out. You would have to look at the kinematics to find out what's happening with those accelerations, right? So this is just an easier way of doing it, a quicker way of doing it, rather. All right. Okay, so let's set this up. So the problem statement tells us that the mass of the rod is equal to what does it say? 5 kilograms. Right. The mass of the disk is equal to 9 kilograms. So for this expression, the weight of the rod is just 5 times gravity, which is 9.81. So that's in newtons. I'll let you guys do the math. I'm just setting the problem up for you. Then you have WD, which is 9 kilograms times 9.81 newtons, right? IR, which is the moment of inertia of the rod about its centroid. You can look at the back of the textbook, you know, your last exam is going to be take home, so you can find these formulas out, but it's just equal to 1/12 times the mass of the rod times the length of the rod. That's if you call that LAB squared like that. So that's just 1/12 times 5 times 0.5 squared, right? And the units for this come out to be kilogram meter squared. Then you have, then you have ID, which is just the moment of inertia of the disk about its center, which is just equal to 1/2 times the mass times the radius squared, right? Yeah, 1/2 mr squared. 1/2 times the mass of the disk times its radius squared. So that's just 1/2 times 9 times 0.2 squared, so kilogram meter squared, like that. All right, so you guys are the math expert. Let's plug in. I'll just give you the final answer. You get that the moment is equal, the magnitude is equal to 99.4 Newton meters. But remember, problem is not asking you for just, it's capitalized M. So it's asking you for the vector, right? So you need to give it a direction. So we assumed that the moment is counterclockwise applied positive. We got a positive answer. So moment is just 99.4 k hat Newton meters. And that's your answer. All right, guys, questions? Is it a lot? Is it making sense? What's happening?
It's making sense for me. I just want to make sure like I always get like that deer in the headlights look when you first start a problem. So you're just like, how do I tackle it? And so I'm trying to like make mental notes of like
So
how
whenever
to.
you're looking at forces and moments, always, always, always free body diagram, kinetic diagram. And that's like 60% of your problem done if you do that correctly. All right. So that's just always do that. This is the easier of the two problems we're doing today, FYI. And your exam is going to be based on one of the tougher problems, the next problem that we're doing. So yeah.
I got one quick question.
Yes.
Could you please reiterate why we had to use a tangential components only?
Yeah, it's not only, it just makes your life easier because when you use tangential and normal components, basically you want to think about using them whenever you have a problem which has pure rotation in it, right? Where everything is purely rotating. Here, that's the case because you have everything rotating about the point A. The reason for doing that is because when you look at the tangential and the normal components, you can find out the tangential component in terms of your angular acceleration, right? Because that's just equal to alpha times r. And the normal component, you don't have to worry about because the normal component just passes through the point about which you're going to find your moments. So it just makes your life easier. You could find out your accelerations in the x and y, but then you'll have to do further equations. You'll have to do kinematics to find out what those components are going to. It's possible, but it's just longer. I'm giving you a shorter method to do it. Does that make sense?
Yes, thank you.
All right, we're good to move on to part B? Awesome. All right. Part B is even simpler because all you need to do is to look at either the rod or the disc. Now, question for you guys is, would you rather look at just the rod or just the disc to find out your force exerted by the pin C?
I would want to say the disc, just because my train of thought is like it's attached to the disc and like has a greater mass. So I figured, just off the top of my head.
Okay. Anyone else?
I feel like it can be either one.
It can be either one, but which one? All right, so you're right. It can be either one. Which one is going to be quicker, right? Because this is dynamics. Okay, that's a terrible joke. But which one is going to be quicker to solve? Looking at the disc or looking at the rod?
Would it be the disc? Because you can just kind of use the parallel axis theorem, right?
You don't even need to do that. You don't even need to look at the parallel. The reason to look at the disc is because then you don't need to worry about the reactions at A. If you look at the rod, then, actually, you know what? That doesn't matter because you can just take the moments about the point A. All right, scratch that question. You can look at either the rod or the disc because I was thinking it's easier to look at the disc because then you don't have to worry about the pin reactions. But again, if you're looking at just the rod and you take your moment about that point, then it's the same thing. So you can look at either one. All right. Sorry for being facetious. All right, so let's look at the disc because that's what I did when I solved the problem. So let's look at disc. And just to bring home the point, can also look at rod and take moments about A. All right, so looking at disk, so let's say that's my disk for my free body diagram, and that's my disk for my kinetic diagram. Right? So now for my free body diagram, looking at the disk, I'm going to have my reaction forces at the pin B, right? So that's going to be Bx and By. I'm going to have the weight of the disk, right? That's just acting downwards. And then at point C, the reaction force is such that it's going to be perpendicular to the point joining C and B, right? Because the spin, it's a slot, right? It's not constrained in two directions. It's only constrained in one direction. So the reaction force at that pin C is just going to be acting on that side and maybe that side, whichever side you have contact on, right? So you only need to worry about the perpendicular reaction force there. So it's only one unknown, basically. That's what I'm trying to say. The direction of it is known. So you can assume that force, let's just call that reaction force C, and that's the one that we have to find. All right, and this distance in the problem, it's given to us for this instant, it's 150 millimeters, right? So this distance here is equal to 0.15 meters. Right? Does that make sense? Okay. Then look at the same thing. Again, pure rotation. Makes sense to look at tangential and normal, but now we're going to see doesn't really make a difference. You can do whatever you want to do. So MD, ADT, MD, ADN, right? And then you have your ID alpha term. All right, and why was I saying it doesn't matter? Because, so if this is the point B, right? All you need to do is just take your moments about, wait, was it B? Yeah, so you just need to take your moments about the point B. Right, so looking at the free body diagram side of things, the only force I need to worry about when I'm taking the moments about the point B is this one here, right? And that's C, that's going to be positive, right? So it's equal to C times 0.15, which is the perpendicular distance. And that, again, I don't need to worry about the moments due to these accelerations. So I'm guessing rod is probably easier, right? Because, sorry, disk is easier now that we're actually solving it. Because if you look at the rod, you'll have to worry about, you won't have to worry about those, but you'll have to worry about this acceleration term, which is okay, right? But it's just more work to do, right? And you'll have the reaction force C over there. So, I mean, you're just adding an extra term in there, basically. And then you'll obviously have the I alpha term too. All right, so looking at the disk is a little bit easier. And that, because I'm looking at the point B, is just equal to ID alpha, like that. That's it. One expression for one unknown, because everything else is known, right? Because ID is known and alpha is given to you in the problem. So you get that solving this expression at the pin, the reaction force there is just equal to 30 newtons. So your direction that you assumed is correct. All right, but again, whenever you're doing it, you're asking out, you have to, whenever you're finding a force or a moment, always write the direction out as well, right? So for the direction, I know that that's like that, it's 30 newtons, right? And I'm told That angle is 90 degrees, and then this angle is equal to 30 degrees. So that means that this angle is equal to 60 degrees, and then that angle there is equal to 60 degrees. So if I write it out as a vector, that's just equal to 30. You have in the x-hat direction, it's minus sine 60 in the i-hat direction, and then it's minus cosine 60 in the j-hat direction. And that's your answer. Does that make sense, guys?
Could you move up a little bit? Yeah, I got that. Yep, thank you.
Questions, concerns, comments?
Is the 30 newtons, is that coming from the mass of the disk?
No, that's just what you get when you solve this expression here. Right? You found out what ID is, right, from here, and you know what alpha is that's given to you in the problem. So you're just one expression for one unknown over here, which is C.
All right.
That's what you're solving for in the problem, the force exerted by the pin C on the member AB.
All right, I see that. Thank you.
Good? All right. This is the next problem. So here, it's very similar to the problem we looked at when we look at the kinematics, and that makes it even better because now this is going to be the kind of problem you get in your exam. All right. You're going to have to look at kinetics and kinematics in one of the problems for the exam when you're looking at moments and forces. All right. All right. So you have two rods, AE and BP, which rotate. There's a collar P, which can slide along AE. The rod attached at A has a weight of 1.6 pounds and a length of 8 inches. And the rod BP weighs 2 pounds and is 10 inches. And there's no friction on this collar, right? It slides frictionally, right? So the motion of the system is controlled by a couple, by a moment, which is applied to the rod BP, right? So let's have that. Let's just set it up. So that's an unknown moment over there, right? So the problem is asking you to find that if in this instant BP is moving at a constant angular velocity of 20 radians per second, excuse me, clockwise, find out the couple moment M, right? And also find out the components of the force exerted on AE by the block P. All right? So that's what the problem is asking us to do. So in this problem, we're going to do the same thing, look at the kinetics, but now it's not straightforward because the accelerations we're going to have to find out by looking at the kinematics. Here, in the previous problem, we applied a big shortcut when we were looking at the accelerations to find out what they were in relation to, because this is everything is in pure rotation. Here, you have not pure rotation, right? You've got essentially two rotations and one sliding motion over here. So this, you have to look at the kinematics. All right, so let's get into it. So looking at the free body diagram first for the rod AE, right, so we have that rod like that. That obviously have to look at the kinetic diagram as well, right? So for the rod AE, you have the spin support at A, right? So you're going to have AX and AY, right? You're going to have the weight, which acts right at the center. So let's call that WAE, right? And what else? What other force are we going to have on it?
PV.
That's right. So there's going to be a force. And what's going to be the direction of that force?
Oh, would it just be up then, or up and down?
No, it's just going to be horizontal at this particular instant, right? Because the collar is sliding up and down. So it's only going to exert a horizontal force on this rod.
Okay, yeah, I got that backwards.
Yeah. Right. So let's say, and let's assume that for this case, it's in the, oh, again, guys, you should always call me out on this. X, Y, Z. All right. Okay. So you have, and let's say that it's acting in that direction. All right. This is now equal to the kinetic diagram. And now we don't know the components of the acceleration, right? We're not given enough information about them. So we have to just assume that your acceleration component. So let me see. So let's call this point the center point of that G. So that's a G, right? So let's say that that's just MAG, right? So this has two components in the X and the Y, right? So it's basically two unknowns at this point. All right, I just wrote it as a vector, right? So if you want to write it as a scalar, you can say that that's M. Let's do it in another color. M AGX, M AGY. But so that's two unknowns, AGX and AGY. But I just wrote it as one expression because it's just, you know, it's this makes life, because we're going to find both of those out when we look at the kinematics. All right. Then you obviously have your IG alpha term, right? So it's about the point G. All right. So again, you know, unless the problem is asking you for reaction forces, you don't need to look at the forces at all, because looking at the forces necessitates you have to look at all the forces. So we can just do, for the intents and purposes, just do moment equilibrium, not equilibrium, sorry, moment kinetics, all right? So let's do that. So we take the moment about, and now we're going to work with vectors in this problem, because we'll use Mathematica, all right? So moment about the point A. All right, so I've got R of P relative to A crossed with my force P, right? And I'm just going to put a minus sign here, and this will make sense why I'm putting a minus sign here, because when we look at the rod BP, we have to take an equal and opposite reaction, right? So I'm just going to make it positive in that one. So I'm just saying that it's minus P over here. And this is just for Mathematica to basically know that, all right, this is the same force, but it's in equal and opposite directions, all right? So that's just minus P over there. All right. And the beauty is I don't need to worry about any other force, right? Because this weight passes through that. Reaction forces passes through the point. So that's it from my free body diagram. This, on the kinetic side of things, is just, so you have your, you know what? I drew this wrong. I want to write like that. IG alpha like that, right? Just assume it's positive because it's unknown. So IG alpha. And now you have to be careful, right? Because AE and BP are going to have different angular accelerations, right? So this is going to be IG alpha AE like that, right? So IG alpha AE like that. Plus the moment due to the translation acceleration, right? So you have that, so you have R of G relative to A crossed with the mass of, so let's say that this is the mass of AE, so mass of AE times the acceleration vector over there. All right, question for you guys. How many equations do I get from this expression?
It'll be 2.
Is it two?
No, it's just 1, right? Because moments, whenever you're looking at planar, rigid body motion in a plane, which is what we're doing in our course, everything is going to come out to be in the k hat direction when you're looking at moments. So you only have one expression from here. Does that make sense, guys? I'll write it out for you. Only one expression as everything in k hat direction. And that doesn't help us, right? Because though we know position vector, we can find out what your IG is from the geometry. You can find out what RG alpha is. We don't know what P is. We don't know what alpha AE is, and we don't know what AG is. So you have, and AG is going to be 2 unknowns. This is like 4 unknowns in one expression. We need more. We need more things. All right, so let's look at, now, you could be tricked into thinking, all right, Ashish, why don't you just do force equilibrium to find out, to add more equations, right? You can't do that because you add 2 expressions, but you also add 2 unknowns, AX and AY. You're not helping your cause by looking at the force the forces, right? Is that clear? All right, so now let's look at the rod BP. All right, so looking at that rod, I'll draw the rod out. So it's, whoops, it's this rod over here, right? So you have free body diagram rod and kinetic diagram rod. All right, so the easy ones, reaction forces out of the way. So Bx, Py, that's right at the pin, right? You also got your applied moment in this case, right? Then you'll have the weight. It's going to act downwards, right? So let's just call that one W, right? And then you have the equal and opposite reaction due to the collar force, right? So this is going to be P like that. All right, and similarly, this guy, let's call this center point here, the centroid for this rod, let's call that H. Right, so similarly, you're going to have an arbitrary acceleration term, because again, you will have 2 components, right? So you have mass of BP like that, and then you have your IH times alpha BP like that. But one simplification we can do, we're told that the rod BP has a constant angular velocity clockwise. So this alpha term is 0. So that term is just equal to 0. So now we do moments about the point B, right? So that's going to be R of P relative to B crossed with your force P, right? And that's And now you get why there's a minus up there, because they're equal and opposite, right? So this is minus p, this is going to be plus p. This is just for Mathematica to know that we're good with our signs. All right. Plus, you have a term for r of h relative to b crossed with your weight of the rod, right? Plus, you have this moment that's acting, right? So you have a moment term, right? And this is equal to, when I'm looking at the kinetic side of things, I just have one expression, right? It's just going to be r of h, this is point h, r of h relative to b crossed with this term here. So you have r of h relative to b crossed with the mass of bp times a h, like that, right? And in this expression, right, that's good, weight you can find out, moment, force p, you don't know, acceleration, you don't know. So you end up with two expressions, but you have a whole lot of more unknowns than you have, right? So what you want to do in these kinds of problems, where you're looking at the moments of the forces and you have accelerations that are happening, is when you look at the kinetics, you can find out all of these terms. You should be able to find out what alpha AE is, you should be able to find out what AG is, and you should be able to find out what AH is, looking at the kinematics of the problem. Because once you do that, you're just left with two expressions for two unknowns, right? With P and M, right? So basically, the setup of the problem is going to be like this. It's going to be like the problems that we looked at last class or the last two classes, but now we're looking at the causes of those motions. So the motion for that particular instant is going to be completely described, which will be allow you to find out all of the accelerations that you need, angular and translational. And then you have to find out the forces that are causing those accelerations. But in order to get to those accelerations at that particular instant, you have to do the first step, which is look at the kinematics of the problem. All right. Does that make sense, guys?
Like I'm still processing it. I'm still like it sounds right. I'm just like trying to like, you know, make sense in my head.
So this problem that you see over here, right? And think of it as being like, you know, forget this part, all right? What would a kinematics problem ask you? They could ask you, find out the acceleration for the point E, right? Find out the acceleration for the point H, find out the angular acceleration of AE, or find out the acceleration of the point G in the middle of the rod, right? These are the kind of questions you will get when you're looking at a pure kinematics problem, right? But here, we need to know these things in order to look at the kinetics. So what I was doing was I showed you, we set up the kinetics, but we showed that we have so many more unknowns in there in terms of the accelerations. So we just have to find that out looking at the kinematics. All right, it's just an additional step of looking at the forces, which we're doing over here. So now we have to describe the motions of BP and AE and find out what all these accelerations are. And that has to do with the kinematics. Does that make sense?
Okay.
Take note, watch the video again, watch the solutions again. You will have a problem which has this exact same procedure, all right, in the exam, problem number 2. The first problem is going to be kinematics, right? That's problem 1. Second problem is going to be kinetics, looking at moments and forces. Third problem is going to be energy conservation, all right? That's the exam, basically. All right. So now we're going to look at the kinematics. All right. So looking at the rod BP, right? Which, all right, let's get this. Give me 1 second. I just want to do something to make life a little easier. All right, so now for the rod BP, right, I can say that the velocity of the point P is going to equal. So now what I'm going to do is, the first thing to do is to find out what alpha AE is going to be. Right? So that's what we're going to do first. And you also need to find out what omega AE is, because those things are going to relate to AG and AH, right? So you're just trying to completely describe the, what's going on with the problem. All right, you'll also have an acceleration of P relative to A as well, right? So that's another thing that you're potentially going to be finding out. All right, so now looking at the velocities, right? You have when I'm looking at the velocity of the point B, put my frame of reference at B, right? VB is equal to 0. Don't need to worry about that. Velocity of point P relative to B, that's equal to 0, right? That length PB does not change, right? So the only term in here that comes into the picture is omega BP crossed with R of P relative to B. All right, and in the problem statement, omega BP is given, right? And we can always find out what RPB is. Similarly, for the acceleration, the only term that comes into the picture, because it's at a constant angular velocity, acceleration of P relative to B, that's 0. Acceleration of B, that's 0. Coriolis acceleration, that's 0, because the length of P relative to B does not change, right? So the only term that you have in here is omega BP crossed with omega BP crossed with R of P relative to B. All right, and again here, everything is known. Now, knowing exactly what point P is doing, you can use that to find out what's happening in the rod AE. That's just what we've been doing in kinematics, right? So if I call this expression 1, I call this expression 2, right? So now I look at rod AE, which is this rod over here, right? For the velocity of the point P, now I'm going to have a term which is velocity of P relative to A, right? That's going to be an unknown. Right? Plus, I'm going to have omega AE crossed with R of P relative to A. And again, here, omega AE is going to be an unknown. Right?
A quick question.
Yes, please.
Should that be VP with respect to A or VP of A? The last equation.
Velocity of P with respect to A, right? Because remember, my velocity equation, when I'm looking at that, is just VP is equal to VP relative to O plus VO plus omega crossed with the r of p relative to O, right? That's my acceleration. So it's this term here. So I've moved my frame to the point A to find out what that is, right? So VO is 0 because
Oh,
point A is fixed. So it's VP
okay,
relative
thank you.
to A.
Yeah,
It's because the call is sliding on that.
thank you.
Yep. So this is equation number 3. Guys, this is tedious, but it's simple, right? It's just the only thing it is tedious. Then similarly, for my acceleration for P, right now, I'm going to have a Coriolis term, right? Because P moves relative to A, right? So I'm going to have 2 omega AE crossed with the velocity of P relative to A, right? I'm going to have my centripetal, whatever you want to call it, term, which is omega AE crossed with omega AE crossed with R of P relative to A. I'm going to have an angular acceleration term, right? Because this one, the angular acceleration, we can't assume it to be 0. So that's alpha AE crossed with R of P relative to A, right? Plus, because the collar slides along there, I'm going to also have an unknown acceleration term, right? And here I have 4 unknowns, right? VP of A is going to be one unknown. Again, I know what the direction is going to be, so only the magnitude is unknown. Omega AE is unknown, right? All rotational stuff, because we're looking at planar motion, everything is just one unknown because the direction is always out of the plane, right? Then you have alpha AE, which is also unknown. Again, we know the direction. It's going to be in the k hat direction, right? And then you have the acceleration of P relative to A. Again, only one unknown because we know the direction. It's just going to be along the rod. So now, by doing 1 equal to 3, and so it's the, RHS, right? Because we're equating the motions of point P. Right, so RHS of 1 equals RHS of 3, right? And RHS of 2 equals the RHS of 4, right? So you have 4 expressions for these 4 unknowns, right? And I'm just going to set it up for you. You can, I'll post the Mathematica solutions online, but we don't have time to go through those. So let's set up the problem. So let's set up the unknowns first. So you have omega AE, set that up as omega k hat radians per second, right? You have alpha AE, which is equal to alpha k hat radians per second squared. So those are 2 unknowns, right? You have acceleration of P with respect to A. Let's just say that that's A. And we know that that acceleration is going to be in the j hat direction, right? That is a j hat feet per second squared, right? And then you have v of P relative to A. Similarly, I'm just going to give it, just call it an unknown U, because I think that's what I use in Mathematica. Again, that's in the j hat direction. So that's that. All right, and I'm also told that the length of the rod BP is 10 inches, and this length here is 8 inches, right? So this length here, I mean, it says that the rod BP is 8 inches, but we're going to assume that this is right at the end, otherwise we don't have enough information. So this is 8 inches. Actually, no, we do have enough information. So that's just, sorry about that. So that length is equal to 10 inches. So that's all the information that we need. So what I mean by that is, that is equal to 30 degrees like that. And I know that this length here is equal to 10 inches, right? Why am I doing this? so I can write out these position vectors for you guys. So we have R of P relative to, this is P, B, and A. So we have R of P relative to A. So you're in the negative J hat direction, and this length is just going to equal 10 inches times sine 30. But remember, because it's in inches, let's convert everything into feet. So you get R of P relative to A is minus 10 divided by 12 times sine 30 in the J hat direction. Right? And then for R of P relative to B, you're going to have two components, both in the negative I hat and the negative J hat direction, right? So you get minus 10 over 12 times cosine 30 I hat plus sine of 30 J hat. And this is in feet. And you're also told in the problem that omega BP is counterclockwise, and it's at 20 constant speed of 20 radians per second. So that's minus 20 K hat radians per second. All right, how you guys doing? Tedious, tedious, tedious. So now we plug everything in and we solve for our unknowns. And I'll just give you the final answer. You can look at, I'll also post the Mathematica notebook, which you can look at. I got, and am I good to move on to the next page? The things I'm concerned with are just the angular stuff, because that's all I need to find out what AG and AH are going to be, right? So omega AE is equal to minus 20 K hat radians per second. And I'm told, and I find out that alpha AE turns out to be minus 692.8 K hat radians per second square, right? And for this one, solved from Mathematica. All right, so now what I'm concerned with, the point G and the point H, right? Because now I can find out what AG is, right? AG, because it's a fixed point on here, right? Again, put my frame of reference at the point A, right? Acceleration of point A is equal to 0. Acceleration of G with respect to A is also 0. Remember, this is not on the collar anymore. G is a fixed point on the rod. So acceleration of G with respect to A is equal to 0, right? So you only, and similarly, because it's a fixed point, there's going to be no Coriolis term because G cannot move with respect to A. So you only have your centrifugal term and your angular acceleration term. So this is just equal to omega AE crossed with omega AE crossed with R of G relative to A plus alpha AE crossed with R of G relative to A. And here we know everything. We found out what omega AE is, and we can obviously find out what the position vectors are, and we know what alpha AE is as well. Similarly, find out for your point H, again, you put your frame of reference at the point B, right? Acceleration of point B is 0. Acceleration of H with respect to B is equal to 0. Coriolis acceleration is equal to 0 because it's not, H is never physically going to move. So there's not going to be a velocity of H with respect to B, right? And you also know that the angular acceleration is 0, right? So there's not going to be an angular acceleration term either. So you only have a centrifugal term, which is omega BP crossed with omega BP crossed with R of H relative to B. And again, here, you know everything. And with that, if you go back to your original expressions, now you know what AG is, now you know what alpha AE is, now you know what AH is. So you have two expressions for two unknowns, looking at your reaction force at P and your unknown moment M. And that's it, problem solved. All right, so what you can do is you can treat this as one expression. You can treat this as another equation. We know that these are just going to give you, you know, they're just to find out what AG and AH are essentially, right? 44, 5, and 6. All right, so find out. And plug into moment. And I'm just going to write out the expressions below again. So what we had was we had R of P relative to A crossed with minus P like that. That was equal to R of G relative to A crossed with the mass of AE times AG like that plus IG for that rod times alpha AE, right? And the second equation was when you're looking at BP, you had R of P relative to B crossed with P, right? And remember, this is the reason because the pin, the collar P is going to have equal and opposite reaction, right? So P over here. That plus you're also going to have a moment term for the weight, right? That was equal to, plus you also have your unknown applied moment, right, which is causing all of this motion. And that is just equal to R of H relative to B crossed with MBP times AH. And guys, if you're getting like, Ashish, where the hell are you getting these equations from? The same equations that we learned initially when we were looking at the kinetics, right? I'm just rewriting them on the last page for you guys. It's these two expressions over here. So these guys here. So you found out what those accelerations are, plug them in here, and I'll give you guys the setup. Right, so we're told that R of G relative to A. Now, when you're looking at R of G, right, you're told that this whole length is 8 inches, right? So G relative to A, that's going to be 4 inches, right? And it's in the negative direction, so that's just minus 4 over 12. J hat feet. Right, then you need to also have R of P relative to A. We found out previously, right, when we looked at this stuff here, R of P relative to B. So we found that out. Next, we need R of H relative to B. That's just, you know, this length here is going to be 5 inches. So you're just taking the components of that. So that is, and again, it's in the negative direction. So you get minus 5 over 12 times cosine 30 I hat plus sine 30 j hat. That's going to be feet, right? You're also told you can find out what IG is, right? That's just equal to, for that one rod, so 1 over 12 times the mass of AE times its length squared. You can find this out, right? This is known. I'm not, you guys can figure that part out. Then we're told what the weight is 2 pounds for this rod BP, right? So that's the one that we're worried with is 2 downwards. right? So that's equal to minus 2 g hat pounds. And for the force P, so this is the unknowns, right? So the unknowns are, say, let's say P, and we assumed it to be in the positive direction, so Pi hat, and the unknown for M, that's just going to be M K hat, right? Because the moment, again, whenever you're looking at moments or angular velocity, angular acceleration, because it's planar, it's always going to be in the K hat direction. All right, you solve all of that, and you get your final answer, which is your moment is equal to minus 5.82 K hat pound feet. And your force P is minus 12.24. So we just assume the wrong direction. I hat pounds. How was that? How was that trip?
Wild, man, wild.